Hello viewers, my name is Dr. Saeed. In this video, I am going to solve this fractional order homogeneous nonlinear differential equation with the help of Adomian decomposition method. I did solve ODEs and PDEs by this very method. I will provide the link in the description so you can have a look and see what are the basics of this method. Okay, first we have to identify our linear operator. We call it L, which will nothing but this very first operator, which is d by dt, and we have to define its L inverse as well. So L inverse here will be, since it is derivative, so L inverse will be integral of some function with respect to t. Again, we have a nonlinear term. We'll call it n of y, which is minus 2y square, but for simplicity I just taking y square. Okay, for under this notation, this differential equation can be written as L of y, and I am shifting the other two terms to the right, so it becomes minus d half by dt half of y, and then 2y square. Now I need to apply the L inverse operator, which is an integral operator on this equation. Since L inverse and L will cancel each other, so I am left with y only on the left hand side, and for the right hand side, since this is an integral operator, applying here it will generate some constant, call it c, and minus L inverse of half derivative of y with respect to t, and then 2 times L inverse of y square. Okay, now since L inverse is an integral operator, so and this is a differential operator, so we have two operators at one term. We can combine them. Index law for fractional integral and fractional differential operator allows us to write it in single operator. So the integral operator is just -1, and this differential operator is half. So combining it will left -1/2. So it's it's a differential operator of order -1/2, or we can say that this is an integral operator of order 1/2. So this is y is equal to c minus, this becomes d to the power -1/2 of y with respect to dt of order -1/2, and the second term will remain as it is. Or we can even write it in our proper notation. So y is equal to c minus I of order 1/2 of y from 0 to t as well, plus 2 times L inverse of y square. Here I of order 1/2 is an Riemann-Liouville integral operator from 0 to t. Okay, now we have to define our y. We have to decompose it under Adomian decomposition method, as we know that y is decomposed as infinite series n from 0 to infinity, which is nothing but y1, y0 plus y1 plus y2 and so on. And we have to retrieve these components in order to get our solution y. So for y we have this decomposition, and for non-linear term we have different decomposition. Non-linear term, which is n of y, is decomposed as summation from n0 to infinity an, where an are Adomian polynomials. So remember, when we are applying Adomian decomposition method, we break y into two different categories. The linear y's are decomposed like this infinite series, and non-linear y's are decomposed by Adomian polynomials. Okay, plugging these values back into equation, I get summation, since y is this series, so summation n from 0 to infinity yn c time integral operator of order 1/2 of y, which is summation n from 0 to infinity yn plus 2 times L inverse of, since it's y square, so it has series n from 0 to infinity of an. Okay, Picking the same terms from this series, we get a recurrence relation, which is y naught is equal to c and y n plus 1 is equal to minus integral of order 1 by 2 of yn and then 2 times L inverse of an for n is greater than or equal to 0. This is our recurrence relation. We'll use this recurrence relation to retrieve the components of y, which are y naught, y1 and so on. Y naught is already given to C, so we need to find other components. And remember, a and are the Adomian polynomials. L inverse is integral operator with respect to t, and this is Riemann-Liouville operator of order 1 by 2. Okay. First, we'll take n is equal to 0. N is equal to 0. For this, we have y1 is equal to minus integral operator of order 1 by 2 of y naught plus 2 times L inverse of a naught. We need to solve this equation to get y1. Here y naught is c, so it's simple. But what about a naught? A naught is a Adomian polynomial of order 0. So we need to find its value first. A naught, the value of an, the general formula is 1 over n factorial dn by d lambda n of summation I from 0 to n lambda to the power I yi and at lambda is equal to 0. For an, we need to put n is equal to 0. So here a naught 1 over 0 factorial, which is 1, d to the power d 0 order derivative is nothing. So n of I from 0 to n, which is again 0, so it will generate only one term for I is equal to 0. So lambda to the power 0 is 1, so here only have y naught. And since n of y non-linear term is y square, so n of y naught is y naught square, and since y naught is c, so it is nothing but c square. Okay, here we have now minus integral operator of order 1 by 2 of y naught, which is c, and then 2 L inverse, which is classical integral operator a naught, which is c square, and d. Okay, one thing is left still. We have to find this thing. This is Riemann-Liouville integral operator of order 1 by 2. The formula is I from 0 to t of order alpha sum t to the power n is equal to gamma of n plus 1 over gamma of n plus alpha plus 1 and t to the power n plus alpha. This is the formula, Riemann-Liouville formula. Here we have only c naught and there is no t, so we can write it integral operator from 0 to t of order alpha is here 1 by 2, and we can write c to the power c into t to the power 0. C can be shifted outside, and the remaining we will use this formula when n is equal to 0 and lambda alpha is equal to half. So this becomes lambda gamma of n plus 1, n is 0, so gamma of 1 over gamma of n plus alpha plus 1, n is 0, alpha half plus 1, half plus 1 3 by 2, so it is gamma 3 by 2 into t to the power n plus alpha, n is 0 and alpha is half. And this becomes gamma of 1 is 0 factorial, which is 1, and gamma 3 by 2 is 1 by 2 into pi square root. So combining it, we get 2 times c into t square root n over pi square root. Remember gamma 3 by 2, the value of gamma 3 by 2 is 1 by 2 gamma pi square root, and this 2 becomes in the numerator, so this is the same 2. Okay, so now we have here minus, this thing has this value 2c square root of t whole over square root of pi, and here we have 2c square into t. This is our y1. This is our second component because we have already known the first component, which is y naught, so c. Okay, now we have to use n is equal to 1. For n is equal to 1, I have
here when n is 1, this becomes y2, and here minus integral of order 1 by 2 of y1, and then we have 2 times L inverse of A1. We need to find this value. Okay, first we'll take this thing. I will first solve this thing, which is integral operator of order 1 by 2 into y1, and this is our y1, minus 2c over square root of pi into t 1 power 1 by 2 and plus 2c square into t. Okay, I will split the integral and put the constant outside, so this becomes minus 2c over pi square root integral operator of order 1 by 2 into t to the power 1 by 2, and then 2c square integral operator of order 1 by 2 into t. Now I will use the same formula for evaluating this integral operator. This is the formula, and here alpha is again 1 by 2, and n for the first term is 1 by 2, and for the second term n is 1. So gamma n plus 1 over gamma n plus alpha plus 1 into t to the power n plus alpha. Okay, I am using this formula to find the value of these two terms. So it is minus 2c over square root of pi into, this is my alpha, this is my n. So this is alpha and this is n. Okay, using the formula gamma n plus 1, so n is 1 by 2 plus 1, so it is gamma 3 by 2 over gamma n plus alpha plus 1. So n plus alpha, half plus half 1 plus 1, which is gamma 2, and then t to the power n plus alpha, n is half, alpha is half, so it is t to the power 1. This is for first term, and for second term 2c square. Here you can see that alpha is again half, but n is here 1. So n is equal to 1 and alpha is equal to 1 by 2. So same formula, gamma n plus 1, gamma n, which is 1 plus 1, so gamma of 2. In the denominator, gamma of n plus alpha plus 1, n plus alpha plus 1. So it's 2 plus half, which is 5 by 2. 5 by 2 and t to the power n plus alpha, 1 plus half, which is 3 by 2. Okay, now this becomes minus 2c over square root of pi into gamma 3 by 2. Remember, gamma of x plus 1 is equal to x times gamma of x. So gamma 3 by 2 is gamma 1 plus 1 by 2, which is 1 by 2, and gamma 1 by 2, which is 1 over 2, and gamma 1 by 2 is square root of pi. So this is square root of pi, 1 by 2 square root of pi, 1 over 2 square root of pi, and gamma 2 is 1 factorial, which is 1, and into we have just t. For second term 2c square, gamma 2 is again 1 and gamma 5 by 2. Using this formula, gamma 5 by 2 is gamma 1 plus 3 by 2, which is 3 by 2 gamma 3 by 2, which is 3 by 2, and gamma 3 by 2 is already 1 by 2 gamma square root. So it's 3 by 4. So it is 3 over 4 gamma square root into t to the power 3 by 2. And this becomes finally, these two cancel out these two, this cancel out this one. So we have minus ct, minus ct from the first term, and for the second, this 4 becomes in the numerator, so 4 times 2, 8. So this is 8 and c square over 3 square root of pi into t to the power 3 by 2. This is my first term. This is my I to the power I of order 1 by 2 of y1. This is this absolute value. And now I need to calculate this thing, 2 times L inverse of a1. Okay, I need to find L inverse of a1.
What is an? An is 1 over n factorial dn by d lambda n of summation I from 0 to n, and lambda power I and yi, and at lambda is equal to 0. For a1 I need to put n is equal to 1. This is 1 over 1 factorial, which is 1, and then we have d by d lambda n of summation from I0 to n, which is 1. So it have only two terms, when I is 0 and when I is 1. When I is 0, it will just y0, and for I is 1, this becomes lambda times y1, and remember we have to put lambda is equal to 0 at the end. Now I have to differentiate it, so it becomes n prime of y plus lambda y1 into y1, because we are differentiating respect to lambda, and then we have to put lambda is equal to 0. So when lambda is equal to 0, this becomes n prime of y into y1, and since n of y, my n of y is equal to y square, so n of y0 becomes y0 square, whose derivative is equal to 2y and into y1. So this is the value of a1. So coming back here, L inverse of a1, which is nothing, just 2y0 into y1, and L inverse is just integral operator, classical integral operator with respect to t, 2y0, and y0 is c, and y1 we have found the value of y1, which is this one, minus 2c t squared over pi squared and plus 2c squared t. So it has minus 2c square root of t over square root of pi plus 2c square t dt. Okay, this becomes integral 2c and then 2c, so it has minus 4c square over square root of pi into t to the power 1 by 2. This is for the first term, and for the second term we have 2 times 2 4 c cube into t with respect to t. Now integrating, I get minus 4c square over square root of pi and 3 power 3 by 2 over 3 by 2, and then 4c cube into t square over 2. This is my, okay, one more step. This becomes 2 times 4, this is minus 8c square over 3 times square root of pi into t to the power 3 by 2, and this is 2c cube t square. Okay, now I have collected and simplified all these two sums. So y2 becomes minus time, so y2 becomes minus time integral of order 1 by 2 of y1, which is this thing minus ct, so it is minus ct and then 8c square over square root of pi, 3 pi and 3 t 3 by 2. Here we have 3 and t to the power 3 by 2, and then we have 2 times L inverse, 2 times, so we have 2 times of this thing, minus 8c square over 3 times square root of pi into t to the power 3 by 2 and plus 2 c cube t square. Okay, this becomes ct and minus 8 c square over 3 square root of pi into t to the power 3 by 2, and this becomes again minus 2 times 8 16 times over 3 times square root of pi c square into t to the power 3 by 2, and then 4 times c cube t square. Okay, second and third terms have the same
power of t, so we can combine it. So this becomes c t, and here minus 8 by 3 and minus 16 by 3, which is minus 24 over 3, which is minus 8. So combining these two terms, I get minus 8 c square over square root of pi into t to the power 3 by 2 plus 4 c cube t square. This is my y2. Okay, I have successfully found 3 components. Since for the next component it will take much calculation, so I'm just leaving it from here. So our assumed solution was y, which have the infinite series y0 plus y1 plus y2 and so on. So y0 is c, y1 is this one, minus 2c, minus 2c over pi square root into t square root, and it has one more term which is 2c square t, and then y2 which has c t minus 8c square over square root of pi t 3 by 2, and then we have 4 c cube t square and plus so on. We can arrange a little bit by the powers of t. So first we have constant term c, and then we have t to the power minus 2c over square root of pi t to the power 1 by 2, this one, and then we can two terms for c, 2c square plus c into t. I just combined this one and this one, and then we have minus 8c square over square root of pi into t to the power 3 by 2, and then 4c cube into t square and plus so on. This is the final answer in the form of infinite series. If you observe, I solved the same differential equation which I solved in my previous lecture by the help of an power series method. Same differential equation, but two different method, power series method in the previous lecture, and here Adomian decomposition method, and you can see that both method generated the same exact solution, which guarantees the correctness of the both method. Thank you for watching.